Hello YouTube, welcome to this installment of the Avion blog. So today we're going to get a little bit more of an exciting project going. We're going to talk a little bit about something called pulse width modulation, or PWM for short. What exactly is PWM? How do we use PWM in electronic circuits? What is the application for it? There's many applications for PWM in electronics, but the main purpose that I'm going to talk about now, well, first we're going to talk about what exactly PWM is. I'm going to show you what PWM is on the oscilloscope, and we're going to generate PWM. I'm just going to use an Arduino because it's simply available, so if anybody wants to follow along, they're welcome to get the Arduino. I'll post a link to the code for this project so you guys could try it at home, etc., and learn a little bit about PWM and how PWM works. PWM is exactly what it sounds like, pulse width modulation. So basically, depending on the output you require, it will give you a different pulse width on your signal. So what that basically means is, let's say you have a range from 0 to 100%. Okay, let's say we're using a 3.3, or let's say a 5 volt, okay, for argument's sake, a 5 volt Arduino microcontroller. Okay, so a PWM output would technically be trying to simulate an analog 0 to 5 volts output. Not exactly what it does, but just to give you an example. So where PWM comes in now is PWM is used a lot in MOSFET gate control. In other words, how wide open you want the MOSFET to run in dimmer circuits, for example. So your MOSFET is like a variable switch. You've got your potential power supply and your globe, and the PWM, depending on the input that you put into the gate of the MOSFET, will open it up slightly, more, whatever the case may be. It works pretty well. We'll actually do that on the breadboard, and I'll scope it out so you can see exactly how everything works. But it's also brilliant for process control applications, for so many different things actually. Now, PWM out of an Arduino operates at 490 Hertz, I believe, if I'm recalling correctly. It's been a while since I've tinkered with it. So what I'm going to do is I'm going to run up some PWM code. We're going to jump across to the computer, and we're going to see how you do that on the Arduino, and then I'm going to show you what the PWM outputs are. But before we do that, let's talk again about the PWM. I got a little bit off track there. So PWM you have from 0 to 100%. So what it means is, at 0 you actually have no digital waveform on the scope, and at 100% you're on all the time. At 50% you'll actually have a perfect 50% square wave. So 50% of the time it's on, 50% of the time it's off. So that would be like a perfect square wave coming out of a signal generator. Would be a 50% duty cycle, if that's what it's set as the baseline. Your sine wave out of your power, a pure sine wave, is a 50% duty cycle, unless there's some serious distortion going on. So if you're running a 25% duty cycle, that means 25% of the time on a one cycle, 25% of it will be on, and the other 75%, so it'll be on, and the other 75% will be off. Okay, so you'll be running a 25% duty cycle if that were the case. But you know what, let me show you this on the scope, because then you'll get a better understanding of it. Now, before we do that, Arduino, this is a little 3.3 volts Pro Mini. It is a 3.3 volt, so your maximum output would be 3.3 volts, and that would be at 100% duty cycle if you were to put a filter on it and measure it and blah blah. In fact, if you put a DC voltmeter on there, you will get a varying voltage depending on the duty cycle you select, and I'll show you that as well. But you need to get a deeper understanding of the actual pulse width modulation and what it looks like and how it affects circuits, etc. I'm really trying to water this down for people that don't understand a lot about electronics, so that they understand a little bit more about duty cycle instead of talking in big technical terms. So that's why I think it's probably good if I show you guys how this works. On the Arduino, you've got a very basic digital to analog converter, which puts out a pulse width modulated signal. So it's not a pure analog signal, but it can be converted into a pure analog signal if the need arises. It will range between 0 and 255. 255 being 100% duty cycle, 127.5 being a 50% duty cycle, and 0 being 0% duty cycle. So you divide that up, like 5 volts divided by 2.5 volts, you'll be at 127.5. So if we tell the Arduino to output 127.5 as a value onto the digital to analog converter, you'll see a 2.5 volts signal out of a 5 volt Arduino. In this case, a 3.3 volt Arduino, you'd see half of the 3.3 volts, so it was at 1.5, 1.65 or something like that, as a 50% duty cycle. The DC voltage will be 1.65, whatever it is. Sorry, I'm just flipping it out at the top of my head. So let's get down now onto the bench, take a look at these things, generate the signal. I'll use one of my portable scopes so you guys can see at all times what we're doing, how the PWM changes, and then you'll get an understanding how the software controls that PWM, and how you can, then we'll step into how you can use that PWM to control the gate of a MOSFET for a very, very raw basic light dimmer circuit, for example, to control an LED's brightness. So we'll do that. But let's step in first and get an understanding of the Arduino side of things. Right, so what you're looking at here is you'll see there's 0 duty cycle showing up, but you'll see 3.38 volts. We're at the maximum, and you'll see a flat line on that rail. Now if I was to run it 127.5 on the Arduino, which would give me a 50% duty cycle, let's upload that. You'll watch it reset, and we'll see what we see here on the oscilloscope. Right, so we've now got a 50% duty cycle, and there we go, it's free-scaled up. So you'll see it's still a peak of 3.3 volts, but you'll now see a 49.8% duty cycle. And your DC voltage is now 1.68. Now remember, we spoke about that halfway mark at 50%. There it is. So now you're seeing a 50% duty cycle, you're seeing the halfway DC voltage being measured, and everything is looking peachy so far. So let's cut you in on the screen so you can see the programming of the Arduino. It's actually very simple to generate these waveforms out of an Arduino. It's actually going to blow your mind. But for an example, in this case it's 2.55 per percent. So if we ran it like at 2.55, we expect to see a 1% duty cycle. And let's see what happens. We'll upload that now to the Arduino, and it'll reset again, and we should see our 1% duty cycle. There it is, 0. Once it settles, 0.8, 0.9, 1% duty cycle, very thin on time over there, and there you have it, and you'll see it's at 0.02 volts of DC at 1% duty cycle. So now you're starting to see a pattern develop with the DC voltage and the actual duty cycle. Now if we ran that to 10%, it would be 25.5 should be expected. So we'll upload it at 10% duty cycle. Now 10% of 3.3 volts, you'll get it now. Okay, we're running at 9.8 or 10%, and 10% of 3.3 volts is 0.33 volts. So there you see the waveform again with these slight little peaks as they go through, and that would now be a 10% duty cycle. I hope you guys are getting some sort of an understanding of the basics of this. This scope is about to go flat, so I'll switch it on to power, and we'll be back and we'll continue with a little bit of a baseline of PWM, but I'll bring you in on the actual screen on the computer so you can see exactly what it is I'm doing and what instructions I'm giving to the Arduino to generate these PWM signals. So when you decide to do your own pulse width modulated control MOSFET drive board for controlling motor speed or light brightness or dimming or whatever, you'll have an understanding of PWM and how it works within the circuit. Now bearing in mind, again, this is a very basic understanding of PWM and how it works, but at least it's a groundwork for you to start playing with PWM and start playing with motor control and bright control, well, basically power control circuits using PWM and many other things. Be right back. Okay, so just to get on to the point about that, I've switched to the PC based scope over here, and you can see the waveform over here. We're still at that 25.5 outputting to pin 9. Here's pretty much the code for the Arduino, by the way. You can put setup details here if you want, your main code here, but all it literally is analog write pin 9 and a value. There it is. there you've got your 10% duty cycle, as can be seen down here on the measurements, 9.8, and we got 337 millivolts, which is our 10% of our 3.3 volts. So now if we were to go to 2.55, which would be our 1% duty cycle, let's do that now. Upload it and then just wait for the Arduino to reset, and we'll see the new waveform appear over here once it's done so. And there it is, 1% duty cycle. It's not even showing it as, but it is, and there's your output. Now, bearing in mind these voltages won't be dead accurate right now, and these PC scopes aren't always so. But for example, now if we took this to full duty, 100% duty cycle, let's do that. At 255 on this microcontroller, we should see a 3.3 volt steady DC. There it is, bang. Well, 3.48, 3.3, more or less close as damn it. And it's not going to show a duty cycle because it's going to appear as DC. But if we now take 255 and we subtract 2.55 from that, so we get a 99%. So let's try that. So we're going to run it at 252.5, 2.5. Let's see if the scope will pick it up. Theoretically, everything should work pretty well. There it is. So you see we're at 98%, well 99% duty cycle, which can be seen down here, and we're almost at peak DC voltage. And you can see we're on and only off for a fraction in time and then back on again. So that kind of gives you an understanding of how pulse width works. Remember we spoke about 50%, let's do that. So we're going to run to 127.5, which we expect to be around 50% duty cycle, or half of 3.3 volts. Let's let that reset, and there it is. We got a 50% duty cycle. 50% of the time it's on, 50% of the time it's off perfectly. And there you've got your half voltage, 1.7, nearly 1.75, whatever it is, and we're running at 50% duty cycle. Pretty simple to see how it all comes together in PWM and how this works. So now you're seeing me control the Arduino here, and you're seeing me scope the output of the Arduino here. Now don't mistake this voltage that you're seeing here for the peak voltage. The peak to peak of this would be 3.3 volts, and the peak would also be 3.3. But the actual effective voltage in a DC circuit would be 1.6, 1.7, 1.8 volts. So yeah, there you have your basic PWM circuit and how the basics of PWM work. So now what we're going to do is we're going to make that PWM actually do some work by driving the gate of an N-channel MOSFET, so you guys can see how that can be used as a power control device. Because bearing in mind, this is only digital signals. It can't control high voltages or high currents or anything like that without some sort of a buffer between the two. And we're going to use a MOSFET as a stage 1 buffer. You can use various devices, but a MOSFET is a varying device, which means it's got varied levels of on and off based on the voltage applied, which will be this mean voltage that we're going to be applying to the gate of the MOSFET effectively. We're actually going to apply the pure PWM, but it's this voltage that's actually going to be the effective part of opening and closing the tap at varied levels. So let's do that next so you guys can see how that works, and then we'll go a step further after that. Okay, so what you're seeing here, now this isn't a proper logic level MOSFET that I'm using, but it'll give you an idea, is we're running at 1 out of 255 on the analog right, which is below 1% duty cycle. If we were now to go to a higher value, such as, let's say 5, you'll see this, once it's kicked in with a higher PWM, this light will increase in brightness. So it's a little bit brighter now with a higher PWM, and then I don't want to go too high because, like I say, not quite the right values. We'll take it to 10 and it'll be even brighter, but then we're starting to push the envelope of this LED without a heatsink, and you're basically getting the gist of how it can control through the MOSFET. Now the circuit, I'm going to put this on a simulator now in Proteus so you guys can see how the circuit functions. in a digital realm, and then you guys can play along on your side and see exactly how these things work. But yeah, that's pretty much the basics of PWM control using a MOSFET. And just to show you again, here we've just got a standard traditional LED connected directly to the PWM output, and you can dim that. Let's just go down to 1% duty cycle. And you'll see as the micro resets, you will see as the microprocessor resets at 1% duty cycle, you're running on a very low level like that. If we take that now and we make that, let's say 30, I'm not sure what that'll be, we'll see now. You'll see this LED will kick in a little bit brighter now, and this is driving directly off the PWM. And that's at nearly 12% duty cycle. So if we go to 25.5, that should be exactly 10%. It'll be roughly exactly as it was. And then we'll go to 51, which will be 20% roughly duty cycle, and you'll see it'll get brighter again. That's at 20% duty cycle. You've got to watch out with these LEDs because they are quite limited by the amount of current that they can contain. So let's go up to 127.5, which is a full 50%, and hopefully we should still be alright, and you should have this LED at almost full brightness then. And there you go. Basic principle just displayed with standard LEDs. Simplest way of looking at PWM. At the moment I've got this USB scope hooked up to the Arduino, and I'm writing the code into the Arduino. Let's just discuss this code over here. It sets the initial brightness to 0. Now remember we discussed that 0 to 255 levels. And then here we've got pin mode 9 as output, pin mode 7 is input pull-up, and 8 is input pull-up. So what that basically means is we're going to go through a 10k resistor to 3.3 volts, and then we're going to ground those pins as we need to get them to go through. So if we want to register basically, so if digital read on pin 7 is low, in other words if it goes to ground, it reduces the brightness by 2.55 or 1% of the duty cycle, and if 8 is pressed, then it'll increase the brightness by 2.55 or 1%. Maximum brightness cutoff is at 255, minimum is at 0, so it doesn't allow it to go any further. And then this just writes the value, and then a small delay so that the buttons don't fly through these in like a millisecond or whatever the case may. You've got 100 milliseconds delay. So if you push them pretty quickly, you'll get quick response. If you push and hold it, it'll run up quite quickly. So let's hit the upload button. Now as we see, it'll start on 0% duty cycle. Now this is a dimmer circuit, a practical application of it. So now I'm going to quickly push the on button, and there you go. You can see we've got a mean voltage increasing, the Arduino at 490 Hertz, and you'll see the duty cycle as I push it again. So you'll start seeing the duty cycle increase, and if you look at the waveform, you can see that. Now I'm pushing it 1, 1, 1. It might be making a few jumps and steps, but now if I push and hold, you'll see it'll climb quite rapidly. I'll stop it about there, nearly 50% duty cycle, and you'll see we're halfway through our 3.3 volt cycle already on the mean voltage. If we go all the way up to 100%, you'll see we'll be sitting at about our 3.3. Now the voltmeter on this thing's not dead accurate, but you get the gist of how it's working. And then if I come down again, or if I push and hold the down button, you can see how it slides through. So now what we got is basically a varying DC mean voltage, which we can use to control the gate, the logic level gate on the MOSFET. Try and pick a logic level MOSFET to get this done. I don't really have any, so I'm having a bit of an issue trying to find some. As soon as I do, we'll put this into practical applications, but there, for all practical intents and purposes, you can see it increase and decrease Now I'm going to throw in a manual LED, and what we're going to do is we're going to increase and decrease and bring in the second camera so you guys can actually see that increase and decrease taking place between the output and ground. So before I do that, I just need to move my scope onto a different point here. Let's run through that one more time. So you'll go up. You'll see as you increase the duty cycle, this LED over here by my thumb will get brighter. I'm not going to go too high again because the LED will probably burn out, and dimmer and brighter, and we'll dim it all the way down nearly at 0 and 0, and she's off. And that's pretty much the basis behind using PWM to control levels. Now the output that you're feeding into this LED over here, you would basically feed into a logic level gate of a logic level MOSFET, and you'll be able to control much higher voltage applications than you would be able to do with the Arduino directly. This just gives you an idea of the simplicity of these things. You can see there, each click it increases by a small margin, or in this case 2.55 or thereabouts. Sometimes it might double up depending on if I hit it like right on the 100 millisecond delay between reading the circuit. But you see it, very simple stuff, guys. Very, very simple stuff.